typical idea of an orbit is an object moving around a planet or other object in a perfect circle with constant speed, but in reality, orbits are much more complicated. Firstly, orbits are not circles. Kepler's first law states that all orbits are actually ellipses, a sort of elongated circle with a long axis and a short axis, with there being many parameters, or orbital elements, that can describe the same ellipse. The most important of these elements being the eccentricity. Eccentricity is a value from 0 to 1 that describes how circular the orbit is. Eccentricity of 0 denotes a perfect circle, and as it approaches 1, the orbit becomes increasingly stretched. When the eccentricity goes above 1, the orbit is no longer an ellipse. Instead, it becomes a hyperbolic trajectory, where the orbit is traveling faster than the escape velocity. An object in an elliptic orbit will speed up as it approaches the lowest point of the orbit, called periapsis, and slow down at the highest point of the orbit, called apoapsis. This happens in such a way where the orbiting object will cover equal areas of the orbit in any equal spans of time, which is Kepler's second law. Additionally, higher orbits require less velocity and will take longer to complete, as the force of gravity lowers farther from the source, and this is Kepler's third law. But this is still just in 2 dimensions. Real orbits occur in 3-dimensional space. But the orbit itself is still a 2-dimensional shape, so it can be thought of as existing in an orbital plane and simply rotated into 3 dimensions. This rotation can be described using 3 angles, the inclination being the vertical rotation of the orbital plane, the longitude of ascending node being its horizontal rotation, and the argument of periapsis representing the orientation of the orbit within its plane. However, orbits don't exist in a vacuum, metaphorically. A satellite in low Earth orbit is also affected by the gravity of the Moon, the Sun, the other planets, and everything else in the universe. A system like this, where multiple objects are mutually affected by each other's gravity, is called an n-body system, and these systems are inherently chaotic, with the only true way to predict a future state of the system being to stimulate it step by step. This can be complicated yet further if there are additional forces such as drag or radiation pressure affecting an object. But this isn't to say that the more basic Keplerian orbits are completely inaccurate and useless. They can still be very useful approximations, as in most cases, the true trajectories will only differ slightly from the ideal, and n-body simulations can be cumbersome and difficult to work with. So while orbits can be much more complicated than you might think, it depends on just how precise you want to be.